Good evening to all reviewers. I'll be presenting our review journal for ISBE. Here are our teams from Faculty of Medicine and Faculty of Engineering. So here's the outline for today's presentation. First of all, we know that the world is facing the crisis due to COVID-19 pandemic, which affect 181 countries, are affecting more than 179 million people who are confirmed to be infected, and more than 3.8 million died as in June 25th, when this review paper is made. And due to this condition, there is literature that estimates that there are 129 billion face masks used every month globally. Or in Indonesia itself, more than 122 million daily. And these masks are made from non-degradable material, which may accumulate and pollute the environment. And this review paper aims to find and compare biodegradable materials that will probably suit and replace current materials to help with environmental issue. And by that, we compare 6 criteria that are we think important, with the reason that I will tell later. The method that we use is literature research from 105 literature and only include 32 literature as reference. And it is the characteristic that I have mentioned before. And first, we discuss the degradation rate, as it is the most important factor that can determine whether the materials are best to overcome mass waste problems or not. And according to recent studies, there are cellulose metal organic framework, or cellulose MOF, which will degrade at 300 degrees Celsius. And there is Janus chitosan that degrades for weeks at room temperature, and then lignin that degrades by 44.5% on 3 days after exposure to a fungus, while starch has only 20% mass remaining after 10 hours of hydrolysis. And then there is PHA that degrades by 98% after 14 days. And there are materials which degrade longer. Those are PLA. It degrades 3 to 5 years. And PLA PBS, which degrades within months, but can be accelerated if it is added with PGA polymer. And as we talk about the mass, it is also important to know the pore size of the used material, because it will also indicate how well particles could pass through the materials. And from the literature, we found that Janus chitosan has 13.1 micrometer and 3.5 micrometer pore size, varying between those. And there is lignin filament that is made by Averroes-Span method using 240 RPM, and it has 35.39 angstrom pore size and 36.01 angstrom if made under 720 RPM. And there is PHA, has pore size ranging from 0.25 to 2 micrometers. And while starch has different pore size depending on what starch it is. Potato starch has 50 micrometer, corn starch 14 micrometer, and wheat starch 20 micrometer. And there is cellulose MOF. It is 1.2 nanometer, or 3.7 nanometer, or 12.2 nanometer, which is the smallest amongst the materials. And then there is also PLA. It is kind of unique because we found that it has 312.8 micrometer filament size, which is kind of big, but it has a small gap between each filament, as it can be seen here, 6.049 micrometer only. And as the purpose of the material is to be used in the pandemic era and beyond, this material is better if they have some degree of antimicrobial performance. As we know that microbes can be spread by direct contact through droplets, warm-aids, skin, or even airborne, making antimicrobial performance become vital to add protection. We divide antimicrobial performance into 3 groups, which are antiviral, antibacterial, and both. antiviral and antibacterial performed in cellulose mold and PLA. While cellulose mold could reduce 60% of virus from different subtypes, including SARS-CoV, and reduce 90% of infectious disease, especially bacteria, for example, Staphylococcus aureus. And also, exposure time also has an impact on the reduction of the infectious disease. Then, PLA can make a virus static and disappear if PLA is being added by ethanol. And this material also has bactericidal performance towards Staphylococcus aureus and E. coli. And also, there are a couple of materials with antibacterial performance. For example, lignin, which can inhibit bacterial growth and damage bacterial cells by making it lysis. And then chitosan lignin contains antioxidant, make it able to hinder bacteria development. And PLA-PBS, which contains lactic acid, which makes it having antibacterial performance toward Bacteria vaginalis. Then PHA, with the addition of glucosamine and chondroitin, also has bactericidal performance. Meanwhile, genus chitosan, equipped with GSW-coated PBS fiber, could attach virus 50 nanometer in size, even after the bacteria is being washed. And the next characteristic is related to long interaction that mouse will have with skin when it's used, and also interact with the respiratory system, which may cause irritation due to immune reaction if there is reaction. That is why this characteristic should be known. Here we can see that cellulose metal organic frameworks do not cause any irritation or even allergic potential reaction under respiratory condition, and even have been tested under ISO 10993. Then genus chitosan does not irritate the skin, tested on rabbit and human, but with different method. And then there is PLA-PBS, which unlikely to irritate the skin because it has been tested using the in vitro assay of skin and the human body. And there is PHA, specifically PHP, which is part of PHA, does not cause any immune or inflammatory reaction on sutured stomach under surgery. Meanwhile, chitosan lignin has chitosan component that can cause allergies and trigger the immune system. Although the lignin component could decrease the inflammatory response, we still need more research on chitosan and lignin. The last criteria that we reviewed is breathing resistance. Breathing resistance will determine if the material is easy to use to breathe or not. The measurement that usually resembles this breathing resistance is the differential pressure. The lower differential pressure is the better material. And the standard surgical face masks usually have differential pressure values between 3 to 5 delta pressure, or 29.4 to 49 pascals per centimeter square. And we found that in PLA, it is 35.78 pascal per centimeter square, and in genus chitosan, it is 59 pascal per centimeter square. But in cellulose mold, it is 2.6 delta pressure, which means easier to breathe than standard surgical masks than other materials. And to conclude all characteristic material that we have been discussed, we find that cellulose, granose, lignin, PBS, PLA, PA, PGA, and also starch has their own unique characteristics which are needed for biodegradable masks. But if we compare for each characteristic, we find that on degradation rate, starch is superior because of its speed on degradation by hydrolysis. And for pore size, antimicrobial performance, immune response, and breathing resistance, we find that cellulose metal organic frameworks seem to perform better than other materials. And also because it has the smallest pore size but still has low breath resistance, it also has antimicrobial performance but does not induce irritation, and even already being tested under ISO 10993 condition. And based on this, it appears that cellulose metal organic framework is the most suitable material for a biodegradable, environmentally friendly mask. However, further studies that involve material techniques such as weighting property and type weighting methods may provide more accurate weighting results. That's all, the presentation for our review paper. Thank you.